Some of you may prefer, instead of me writing on a whiteboard, just a more formally written out proof. So this is what I did here. The idea is to prove the maximum likelihood estimator for the mean and variance of a normally distributed random variable. So that's what I'm doing here. The definition of a likelihood function, I'll give you this really nice definition. Given the data, considering the probability distribution, the likelihood function is the probability of the data conditioned on the unknown parameters. The maximum likelihood estimator is the function that maximizes the likelihood of those data. So that's what we need to find, is what's the function that maximizes the likelihood of those data. So here's this is the probability density function that we're working with. It includes two unknown parameters, mu and sigma square. Right? Parameters are population values, whereas statistics are sample values that are meant to estimate population parameters. That's why we say, we call statistics inferential statistics. We're making these inferences. We'll let theta 1 equal mu and theta 2 equal sigma square, variance. And this is being done to help reduce the burden in the derivation or taking derivatives of the calculus process. So here we have this random variable, and we have two parameters for this normal distribution. If you're not familiar with the normal distribution, this is it, although this has changed a little. Usually you have square root of 2 pi sigma for the standard deviation, but because the theta 2 represents the variance, to get it to be a standard deviation, I had to change this a little bit. Oh, excuse me, because this, I'm sorry, because let me just say, because this represents the variance, I had to square the square root of 2 pi and make it 2 pi. Sorry, I was thinking something different for a second here. So this is the maximum likelihood function, as I showed in the video yesterday. Here, it's a product term, right? Because it's the probability of each result, right? Each value in my sample. So the probability that Joe scored 3 and Eduardo scored 5 and whoever, right, scored 7. So it's these and means that we're multiplying these probabilities. And since this comes from a normally distributed random variable and all these values are identically and independently distributed, we can just go ahead and take the product of them from 1 to n, because there's n different individuals in the sample. And you'll see that this is just a way of simplifying this equation. When we take the product, and here we have this exponent here, that's actually a summation. So if you're not familiar with that, you should read about that in your whatever your math textbook is. It just makes everything a lot easier. Then we take the log, so we don't have to deal. So here we have product terms, 1, 2, 3 different product terms. If we take the log, we don't have to deal with the product terms. Instead, we have additions and subtractions, right? So it makes life a lot easier then. So we're taking that log. Here, the log of L represents a natural log, the ln if you prefer. So log base e, and this is your e right here. When we take the log, we get, and if you're not real familiar with how to do this, you should read about it. Taking the log of a number, it's raised to some power. So this is the output here. Again, read the definitions of logs if you're not sure why I'm doing this. So now we take the derivatives, and with respect to, there's two parameters, so we have to take one derivative with respect to theta 2, and then one with respect to theta 1, so we'll do one at a time. So this is dealing with the variance first. So I take that derivative, and this is because we're dealing with logs here. So this is what this first term just doesn't have any theta 2, so it can just like disappear, right? So it's just 0, and then so we just do these derivatives here. And when we're done, we set this first derivative to 0, because the first derivative is a slope of a line. And when the slope is 0, it means we have a horizontal line, and that's going to be either a maximum or a minimum. So in this case, we set it equal to 0, and then we solve for the parameter we're interested in. In this case, we're looking at theta 2. So we basically just solve for theta 2. Now this becomes just algebra. And there we go. We substitute back the sigma square for theta 2, and we get our known definition of a variance, right? Population variance. So that's our MLE, maximum likelihood estimator. Now we solve for theta 1, which is the mean in this case. We're basically using the same, we start with the same likelihood function and we take its derivative with respect to theta 1 instead. Once we're done with the derivative, we get summation of xi. Well, the reason we have the n here is because it's a sum of this constant here, so it's n times x. I think it's just n of them, right? Okay, and wow, it makes it nice and easy for us, right? By the way, I multiplied by theta 2 here to get rid of this theta 2, right, in the denominator. I wanted to get rid of that. So you multiply both sides by theta 2. This side and the 0 side is going to be 0, so we were left with what looks like a very familiar pre-final equation. Then again, through algebra, we solve for theta 1 and we get mu is equal to, well, this is what our definition of the mean is. And then just to check that what we have is a maximum. So a maximum, the second derivative would have to be negative. Just take the second derivative. And it is negative, minus n. And here, that's for with respect to theta 2, and with respect to theta 1, I get the same thing. So it's a maximum if the second derivative is negative, and it's a minimum if the second derivative is positive. So that is where we started, right? We wanted to show that the maximum likelihood estimate of the mean was, well, we want to show what it is, but we already kind of know this, because that's what we use to calculate the mean. It's sigma xi over n, and then we know what the maximum likelihood estimate of the variance is. And then, of course, in other videos linked to this video, the last video that I just posted, you can see where I prove that sigma xi minus the mean squared is, I should probably put this here as mean, right? Let me make it look nicer, wouldn't it? Let me just insert that in here for you. So make it look more correct, because I didn't change it there. But I show you what happens when we're taking the sample value and why, there you go, why dividing by n, why we divide by n minus 1, and how that's an unbiased estimator of the variance. Did I do that here? Everything else is fine. All right, thank you. Excellent.